All right, time to talk about something kind of different. Suppose y equals log of x. Okay, this is a common logarithm, log base 10. Okay, input is x, output is y, right? What if the input is doubled? Okay, well then, let's represent that doubling of the input. Let's represent that by just taking our x and multiplying it by 2. A doubling of the input, okay? Well, we know now from our log properties that this can be rewritten as a sum of logarithms. So this is like log of 2 plus log of x. So comparing to what we had originally, before we did the doubling, it was originally just log of x. Now, after doubling our input, we have log of x plus log of 2. So if you have a log function, doubling the input actually doesn't do any multiplication to the output. What it does is it just adds a value to the output. Okay, so here we see that y has increased by log of 2, which, by the way, common log of 2, log base 10 of 2, is approximately 0.3. Okay, that's you can ask your calculator that. This is kind of like what I was talking about with like a natural log of any integer. It's going to give you an irrational number. That actually happens a lot with logarithms, even logs with an integer base. If the number that you are giving as an input is not a power of the base, then you're likely to get an irrational number. So I've just rounded this off to the one decimal place. It's about 0.3. So that's what happens if it's doubled. If input is multiplied by 10, what happens? Y equals log of 10x, right? Well then, that's log of 10 plus log of x. And log of 10, since we're dealing with common log here, it's log base 10 of 10. That part equals 1. So then we have y equals 1 plus log of x. So when you multiply your input by 10, then what you do is you just add 1. Y has increased by 1. Okay. Let's flip that around. If input is divided by 10, then what happens is we'll have log y equals log of x divided by 10. And now we can write that as log of x minus log of 10, which is like saying you've got your log of x minus 1. So if multiplying by 10 increases the value by 1, and that's because this is common log, right? So log base 10. Then dividing by 10 is going to subtract 1 from the value, okay? So y has decreased by 1. Now I did it with doubling as well, just to show you, that basically multiplying your input by some number is going to add to the output, and dividing your input by a number is going to subtract from the output. And by a number, I mean like an integer, like a positive, a number bigger than 1. So logarithms have this property of basically turning multiplication or division into addition and subtraction. So for some science applications, a lot of science applications actually, you'll see something called a log scale. And you'll hear people talking about log scales. And a log scale is like a scale you might see on a graph, where increasing along that graph by regular intervals, instead of adding a certain amount every time, multiplies by a certain amount every time. So like 1, and then 10, and then 100, and you can see we've basically increased along our scale by 1, but instead of actually increasing by 1, what we're doing is multiplying by 10, right? Because we're thinking about the log of these numbers down here, producing an increase of 1 every time. Okay, so then for the next increase of 1, we're going to multiply by 10 and get 1,000, and then it'd be 10,000, and so on, 100,000. Okay. ... So whenever you see a scale on a graph which is increasing by multiples, it could be multiples of 2 or multiples of 10, like this. Those are probably the most common ones. Whenever you see those, increasing by multiples for every regular step of the same distance, that's a log scale, and they do that because of this property, right? This algebraic property, and because it turns out that in reality, a lot of measurements, actually, it makes sense to use log functions when measuring things, in part because the way we perceive our reality is in some ways logarithmic. So I'm going to go on a little tangent here, but hopefully we'll come back to this topic in a later video. What turns out that like the way that your brain interprets stimuli is logarithmic. So it interprets a multiplicative change in the magnitude of a stimulus. Like, for example, lifting a 1 pound weight versus lifting a 10 pound weight. Your brain and your nerves basically like interpret that difference as an adding a certain amount. So then multiplying a 100 pound weight would feel the same amount harder than, as compared to the 10 pound weight, that the 10 pound weight felt as compared to the 1 pound weight. So your brain is interpreting these multiplicative changes basically as linear changes. It's like your brain is doing a logarithm of the input and then producing like a linear increase in the perceived magnitude of the stimulus. Same thing with like loudness. When your ear perceives how loud a sound is, it's really like doing a logarithm of that. It's really like your brain is kind of doing a logarithm of that stimulus and then perceiving it like a linear increase instead of a multiplicative increase. And that's why like a lot of scales that people measure things on in science are log scales. So like the loudness of a sound is measured with the decibel scale, which is a log scale, because that's how your brain interprets things with logarithms. The pH of water is measured with a log scale. The magnitude of an earthquake is measured with a log scale. Okay, the Richter scale. So all these scales in science are logarithmic, and I just wanted to kind of put that out there and introduce this idea of a log scale and show you the algebra behind it, so that you understand what that is. Okay, you have some notion of where that comes from. All right, time for new stuff.